Hello everyone, I'm Sonali Basak. Have you ever just stopped and wondered how your smartphone can do so much, and yet it fits right in your pocket? Well, the answer isn't really magic. It's a science that's so small it plays by a completely different set of rules. Today, we're going to dive deep into that invisible world, the world of nanoelectronics. Just think about it for a second. Your phone is a complete powerhouse. It's a supercomputer, it's a professional-grade camera, it's your connection to the entire world, and it's all packed into this slim little device. How is that even possible? Well, it's not just about clever engineering. It's about a whole new world of physics at play.
That's right. The secret lies at a scale that is 1 billion times smaller than what our eyes can see. This is a world so tiny that the physics we learned in school, classical physics, it just doesn't apply anymore. Down here, the wonderfully strange rules of quantum mechanics are in charge of everything. Okay, so let's get into it.
To build these amazing nano devices, we first have to understand how electrons behave inside different materials. It's all about their energy levels. Think of it like learning the floor plan of the building where all the electrons live and work.
So let's picture any material as a huge apartment building just for electrons. Most of them, they're just resting on the ground floor. Very comfortable, very stable. In physics, we call this low-energy floor the valence band. Here, the electrons are just bound to their atoms, not really going anywhere, just chilling out.
But all the exciting stuff, all the real action, that happens on the top floor. This is the conduction band. When an electron gets enough energy to make it up here, it's suddenly free to move around, carry a current, and actually power our devices. It's like the rooftop party where all the important work gets done.
Now, of course, an electron can't just magically appear at the rooftop party. It has to climb the stairs, and that climb takes a very specific amount of energy. That energy cost, as you can see here, is called the band gap. This one single number is what determines if a material will conduct electricity easily or not, and that is absolutely key to building any electronic device.
And here is where the real nano magic begins. When we take our material, our electron apartment building, and we shrink it down to the nanoscale, something amazing happens. The band gap, the distance between the floors, it actually gets wider. Why? Because when you trap electrons in such a tiny space, their energy levels get pushed further apart. This effect, where a material's properties change just because it's so incredibly small, it's called quantum confinement.
So let's just pause and remember the most important point here. It's all about that climb. So what is it that determines if an electron's journey to the work floor is going to be an easy one or a difficult one?
Okay, so we know that electrons need energy to jump that band gap. But how they make that jump? Well, it turns out there are two very different ways. And this difference is what decides if a material is better for making light, like in your phone screen, or for processing information, like in its chip.
We classify semiconductors into two main types, direct and indirect band gap. And the biggest difference between them is something called momentum, which we represent with the letter K. In a direct material, an electron can jump straight up to the conduction band. No change in momentum needed. But in an indirect material, it needs a little extra help to change its momentum and its energy to make that same jump. And this one tiny detail, it changes everything.
Think of a direct band gap like a batsman hitting a perfect, clean 6. The energy transfer is direct, it's efficient, and it's powerful. An electron absorbs some energy, jumps straight up, and when it falls back down, it releases that energy perfectly as a particle of light, what we call a photon. Simple and elegant.
And because they are so good at turning electricity directly into light, materials like gallium arsenide are the superstars of optoelectronics. All those beautiful, bright LED lights you see during Diwali, the powerful lasers in our fiber optic systems, even solar cells, they all depend on this clean, direct transition. Now, an indirect band gap, well, that's more like taking a quick run between the wickets. It's a two-step process. For the electron to jump the gap, it needs energy, sure, but it also needs some help to change its momentum. That help comes from a tiny vibration in the material itself, which we call a phonon. It's like the material gives the electron a little nudge to help it complete the journey.
And this perfectly explains why silicon is the undisputed king of electronics. You see, it's an indirect band gap material, which means it's actually terrible at producing light. But we don't want our computer chips to glow, do we? We want them to be stable, reliable, and efficient at processing information. And for that, silicon is just perfect. So let's think about that again. It all makes sense now, right? Why do we choose a material that's brilliant at making light for our LEDs, but a completely different material, one that's awful at it, to be the brain of all our computers?
So, we've learned how electrons get the energy to work, and we know the two different ways they can make the jump. Now, let's look at how they actually travel from point A to point B, because at the nanoscale, even that journey becomes something extraordinary.
You see, in a normal, everyday wire, an electron's journey is like driving in peak city traffic. You're constantly stopping, starting, bumping into things. That's what causes electrical resistance. But what if we can make the device so short that the electron zips from one end to the other without a single collision? Well, that perfect, smooth journey is called ballistic transport. It's the ultimate electronic expressway.
And the golden rule to make this happen is actually very simple. This magical expressway opens up when the length of the device, which we call L, is shorter than the electron's mean free path, or lambda. And the mean free path is just the average distance an electron can travel before it bumps into something. So if the road is shorter than the distance between traffic jams, you get a clear run. And here's an easy way to remember it. When length is low, electrons just flow.
Now, just think about that for a moment. If there are no collisions, there's almost no resistance, and no energy wasted as heat. So how does building our devices on this single principle unlock the super fast, super efficient electronics of the future?
All right, we've covered the quantum rules, the changing band gaps, the two ways electrons climb, and their expressways. Now for the really fun part. Let's take a peek into the future and see what incredible devices engineers are building with this knowledge right now.
And this isn't science fiction. This is happening in labs today. We're talking about carbon nanotube transistors for computers that are thousands of times faster, graphene devices for almost instantaneous communication. We're even building single electron transistors that control one single electron at a time for ultimate efficiency. And all of this work, it's paving the way for the ultimate goal, quantum computing, a revolution that will change our world forever.
I want to leave you with this thought. Everything we have discussed today, band gaps, quantum confinement, ballistic transport, this isn't just theory to memorize for an exam. This is the fundamental language of our modern world. Understanding these principles is like learning the alphabet for the next great technological revolution. These are the building blocks you will use to design and create a future that we can't even begin to imagine yet. So as you move forward, I want you to keep this question in your mind. You now have the keys to this invisible kingdom. You understand the quantum rules. The future of nanoelectronics, well, it's in your hands. So go out there and create something amazing. Thank you for